Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you've found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the question of whether a visitor from beyond our solar system might bend the very light we use to see. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. The object appears first as a smudge of movement against stars that have held their positions for millennia. Astronomers notice it in late 2025, a point of reflected sunlight traveling through the outer solar system at a velocity that doesn't match anything born here. The numbers accumulate slowly: measurements of position, calculations of trajectory, estimations of speed. Within weeks, the conclusion becomes unavoidable. This visitor originates from interstellar space, from regions where the sun's gravity has never reached, where the architecture of matter belongs to other stars or to no star at all. They designate it 3I Atlas, the third confirmed interstellar object detected from Earth. The I stands for interstellar, a category that didn't exist in astronomical nomenclature until 2017, when Oumuamua forced humanity to create new language for things passing through rather than orbiting. Atlas refers to the survey system that first captured its light. The Asteroid Terrestrial Impact Last Alert System, a network of telescopes in Hawaii and Chile designed to watch for objects that might threaten Earth. Instead, it finds something that will never return, something on a hyperbolic trajectory that carries it through our neighborhood once and only once. The object moves through Taurus, then shifts toward Gemini, its path curving slightly as the sun's gravity tugs at it without capturing it. The hyperbolic excess velocity, the speed it would retain even at infinite distance from the sun, suggests an origin in another stellar system. Perhaps ejected during planetary formation when gravitational interactions flung debris into the dark, or perhaps it condensed from interstellar gas between stars, an orphan born in the void itself. The uncertainty lingers in every observation, in every spectrum taken of its faint light. It measures perhaps 2 kilometers across, possibly smaller, its exact dimensions obscured by distance and the weakness of reflected sunlight at 5 astronomical units from Earth. For context, that's 5 times the distance from Earth to the Sun, far beyond Mars, but not yet reaching Jupiter. The object remains cold, unlit except by the sun's distant glow, its surface reflecting perhaps 4% of incident light, dark as charcoal, dark as ancient ice, mixed with organic compounds that have never felt warmth. Scientists request telescope time, filing proposals to observe this visitor before it recedes beyond detection. Every night of observation becomes precious. The object will brighten slightly as it approaches perihelion, its closest point to the sun, before dimming again as it departs. There's a window, narrow and closing, to gather data about something that has traveled for millions of years to pass through this particular volume of space at this particular moment. And then someone asks the question, could it be lensing background stars? Could its mass be sufficient to bend the light from objects behind it, creating distortions in the sky visible from Earth? The question arrives gently, almost as an afterthought in a research meeting. Gravitational lensing. The bending of light by massive objects has become routine in cosmology. Galaxy clusters lens distant quasars. Black holes warp space-time into visible rings. Even the sun creates measurable deflections during solar eclipses. but a small interstellar object, something perhaps the size of a city block or a mountain, creating lensing effects detectable across billions of kilometers. The scale seems wrong, the mass insufficient, yet the question persists. Because uncertainty is what science feeds on, what it transforms into measurement. The idea spreads through informal channels, emails between colleagues, mentions in Slack channels devoted to small body astronomy, brief exchanges at virtual conferences. Could we detect it? What would we look for? Would the background stars appear to shift position as 3i Atlas passes in front of them? Would they brighten momentarily? Their light focused by the object's gravitational field. The mathematics involved are well established, derived from Einstein's field equations, tested across decades of observation, mass curves, space-time. Light follows those curves. The amount of bending depends on mass, distance, and geometry. The alignment between observer, lens, and background source. For visible effects, you generally need either extraordinary mass or extraordinary alignment, and preferably both. 3i Atlas possesses neither. Its mass remains unknown, but can be estimated from its size and likely composition if it's icy. Perhaps a few trillion kilograms. If rocky, perhaps 10 times that. Impressive by terrestrial standards, utterly negligible by cosmic ones. The Earth masses 6 trillion kilograms. The Sun masses 2 million trillion kilograms. Against these numbers, 3i Atlas barely registers as a gravitational presence. But science proceeds not through dismissal, but through calculation. Someone will do the math, will model the deflection angles, will determine whether any observable effect could exist. Someone will check, because checking is what separates speculation from knowledge, because the universe has surprised us before with phenomena that seemed impossible until they weren't. The object continues its journey, indifferent to human curiosity. It doesn't know it's being watched, doesn't know that electromagnetic radiation from its surface travels to Earth where machines decode it into knowledge. Took 4.5 billion years for this solar system to produce beings capable of noticing interstellar visitors. Took another few million for those beings to develop mathematics sophisticated enough to ask whether the visitor bends starlight. And now the question hangs in the digital air, waiting for someone to answer it with precision. The stars behind 3i Atlas remain fixed in their positions, their light traveling across parsecs to reach Earth. If that light is being bent, the bending is subtle, hidden within the noise of atmospheric turbulence and instrumental limitations. But hidden doesn't mean absent, and subtle doesn't mean impossible. The only way to know is to look, to measure, to compare the positions of stars before and during and after the object's passage. And so the observations begin, quietly, without fanfare, just another set of coordinates added to observation cues at telescopes around the world. Space-time is not empty. This revelation arrives slowly through Einstein's equations in 1915, a mathematical description of gravity that replaces Newton's instantaneous force with something stranger and more fundamental, the geometry of existence itself. Mass doesn't pull on other mass across empty void. Instead, mass curves the fabric of space-time, and objects move along the straightest possible paths through that curved geometry. What appears as gravitational attraction is actually inertial motion through warped space. The analogy often used involves a stretched rubber sheet with a heavy ball placed at its center, creating a depression into which smaller objects roll. But this analogy fails in critical ways. It suggests gravity pulls downward, requires a pre-existing gravitational field to demonstrate gravity, and depicts space as two-dimensional when it actually possesses 3 spatial dimensions plus time. Still, The image persists because humans need metaphors to grasp what mathematics describes perfectly, but words capture only approximately. In reality, massive objects create curvature in all directions simultaneously. The sun doesn't just dimple space beneath it, it warps space-time in a spherical pattern extending outward in every direction, gradually weakening with distance but never quite reaching zero. Earth moves through this curved geometry at roughly 30 kilometers per second, following what's called a geodesic, the equivalent of a straight line in curved space-time. We experience this geodesic motion as an orbit, as the year-long circuit that brings seasons and solstices and the slow precession of equinoxes. Light also follows geodesics through curved space-time. Photons have no mass but possess energy, and energy couples to space-time curvature just as mass does. When light passes near a massive object, its path bends. The bending is slight. The sun deflects light from distant stars by approximately 1.75 arcseconds at its limb, roughly 1/2000th of a degree. Only detectable during solar eclipses when the sun's overwhelming brightness doesn't wash out nearby stars. Only measurable with careful photography and precise comparison to star positions when the sun occupies a different part of the sky. This deflection makes the sun a lens, albeit a weak one. A lens redirects light, focuses it, changes its path. Glass lenses accomplish this through refraction, light slowing and bending as it passes through denser material. Gravitational lenses accomplish it through space-time curvature light, maintaining constant speed, but following curved paths through warped geometry. The mechanism differs, but the optical effect remains similar. Background objects appear in different positions than they would without the intervening mass. For 3i Atlas to act as a gravitational lens, it must possess sufficient mass to curve space-time measurably. The deflection angle for a point mass is given by a straightforward equation 4 times. The gravitational constant times the mass, divided by the speed of light squared times the impact parameter, the closest distance between the light ray and the lensing mass. The formula reveals an uncomfortable truth. Deflection scales linearly with mass, but inversely with distance. Double the mass, double the deflection, double the closest approach distance, halve the deflection. Consider the numbers for 3i Atlas. If it masses 10 trillion kilograms, a generous estimate, and light passes within 100 kilometers of its center, the deflection angle calculates to approximately 10 to the negative 14 radians. That's 0.2 degrees, or about 2 millionths of an arcsecond. For comparison, the best ground-based telescopes achieve angular resolution around 1 arcsecond under ideal conditions. Space-based instruments like Gaia reach micro-arcsecond precision for bright stars, but only through years of repeated measurements and sophisticated error correction. 2 millionths of an arcsecond sits far below detectability, lost in atmospheric shimmer and instrumental noise and the quantum uncertainty of photon arrival times. Even if 3i Atlas possessed 1,000 times more mass, making it a small moon rather than a large asteroid, the deflection would barely graze the threshold of possibility with current technology. But lensing creates other observable effects beyond simple position shifts. When alignment becomes particularly precise, when source, lens, and observer arrange themselves in nearly perfect linear configuration, the background object's light can be magnified. The lens focuses light that would otherwise miss Earth, concentrating photons that would have passed above or below or beside our planet. This magnification makes distant objects temporarily brighter, sometimes dramatically so. The brightening follows predictable patterns. For a perfect alignment, where the background source sits directly behind the lens. Light bends around all sides of the lensing mass equally, creating a ring of light called an Einstein ring. For slightly imperfect alignments, the ring breaks into multiple images, typically 2, sometimes 4, occasionally more, depending on the lens's mass distribution. For very imperfect alignments, only magnification occurs without visible image splitting, a single brightening event as the lens passes between observer and source. These microlensing events happen regularly in our galaxy. Stars in the foreground pass in front of more distant stars, creating brightening events that last hours to months, depending on the lens mass and relative velocities. Astronomers use these events to find planets orbiting the lensing star. The planet creates a brief, additional brightening spike superimposed on the stellar microlensing curve. Thousands of such events have been detected, catalogued, analyzed for information about galactic structure and planetary abundance. Could 3i Atlas create a microlensing event? The geometry seems wrong. Microlensing requires the background source, lens, and observer to align within an angle smaller than the Einstein radius, a characteristic angular scale that depends on lens mass and distances involved. For stellar microlensing, Einstein radii typically measure merely arcseconds, achievable because galactic distances stretch across kiloparsecs and stellar masses run to solar values. For 3i Atlas, the Einstein radius calculates to something near 10 to the negative 8 arcseconds 10 billionths of a degree. The object would need to pass within that angle of a background star's apparent position for any magnification to occur. Given that 3i Atlas moves across the sky at rates measured in arcseconds per day, and given that background stars are separated by arc minutes at minimum, the probability of such an alignment approaches but never quite reaches zero. Still, improbability isn't impossibility. The universe contains perhaps a trillion stars within observable range, and 3u Atlas will pass in front of some portion of sky containing thousands of them, if even one alignment occurs with the necessary precision. A detector might record a brief fluctuation in starlight, a temporary increase in photon flux lasting seconds or minutes before the geometry shifts and the light returns to normal. The search for such events requires continuous monitoring. Automated surveys already do this, watching millions of stars simultaneously for any brightness variation. Supernovae, variable stars, eclipsing binaries, microlensing events all create characteristic light curves that algorithms can recognize. Adding 3i Atlas to the watch list costs nothing except computational time. A few extra processor cycles to check whether any stars along its trajectory brighten unexpectedly. And so the object moves through space, warping space-time by amounts too small to measure, creating curvature that exists in principle but vanishes in practice beneath instrumental limitations and cosmic noise. The mathematics remains perfect and precise. The physical effect remains real, confirmed by countless observations of more massive lenses. But reality insists on scale, on proportion, on the relationship between theoretical possibility and practical detectability. Only took a century to progress from confirming gravitational lensing exists to using it routinely as an astronomical tool. Only took another few decades to make the measurements precise enough that even planetary mass objects become detectable through their gravitational influence on light. And yet, a small interstellar visitor, something that traveled for eons to reach our solar system, remains too insignificant to bend the sky in ways our instruments can perceive. The year is 1919, and 2 British expeditions travel to opposite sides of the Earth, carrying photographic equipment and a prediction. Arthur Eddington leads one team to Principe, an island off the west coast of Africa. Andrew Crommelin leads the other to Sobral in northern Brazil. Both arrive months before the event they've come to observe, settling into temporary accommodations, testing their instruments, waiting for May 29th when a total solar eclipse will darken the sky and reveal stars normally invisible in daytime. Einstein's general theory of relativity, published 4 years earlier during the chaos of World War I, predicts that the sun's mass will bend starlight passing near its limb. The amount of bending. 1. 75 arcseconds differs from the value Newtonian physics would predict if light possessed mass and experienced gravity as particles do. Newton's theory suggests 0.875 arcseconds, exactly half Einstein's value. The difference is small but measurable. If someone can photograph stars near the sun's edge during totality and compare their positions to photographs taken months later when the sun occupies a different constellation, the eclipse proceeds as celestial mechanics demands. The moon's shadow sweeps across the Atlantic at thousands of kilometers per hour, reaching Sobral first, then Principe. For a few minutes, the solar corona becomes visible pearly white streamers extending millions of kilometers into space, normally overwhelmed by the photosphere's brightness. And beside the eclipsed sun, stars appear. The Hyades cluster in Taurus becomes visible, its members bright enough to photograph despite the remaining coronal glow. Eddington's team captures usable images despite clouds. Crommelin's team obtains clearer photographs. Both sets of data require months of careful analysis, measuring star positions on the eclipse plates, comparing them to reference photographs, correcting for optical distortions and atmospheric refraction and the various systematic errors that plague astrometry. The work proceeds slowly through summer and autumn, tables of numbers accumulating, uncertainties estimated and debated. The announcement comes in November at a joint meeting of the Royal Society and Royal Astronomical Society in London. The stars near the sun appear displaced outward from their normal positions by amounts consistent with Einstein's predictions. Light bends around the sun. Space-time curves. Newtonian gravity. Accurate enough for planetary orbits and falling apples. Fails at this level of precision. The newspapers proclaim revolution in physics, though most readers can't grasp what it means that space itself possesses geometry. What the 1919 eclipse proves is that mass acts as an optical element, that gravity can redirect light, that the universe contains natural lenses formed not from glass or water, but from the warped fabric of existence itself. The implications unfold slowly over subsequent decades as astronomers begin recognizing lensing effects in various contexts. Radio sources split into multiple images by foreground galaxies, quasars brightened and distorted by galaxy clusters, even the possibility of using the sun itself as a telescope to magnify objects beyond our solar system. The sun's lensing effect is permanent and universal. Every photon passing near it bends by the same formula, following geodesics through the sun's space-time curvature. If you could position a telescope 550 astronomical units from the sun, about 14 times Neptune's distance, well into the Kuiper belt, and align it perfectly so the sun sits between you and a distant object, the sun would focus light from that object, magnifying it enormously. The focal line extends infinitely outward from that point, creating opportunities for imaging distant worlds and galaxies with unprecedented resolution. No spacecraft has yet reached that distance with functioning instruments. Voyager 1, currently the most distant human-made object, crossed 550 AU only recently after 47 years of travel. Its cameras stopped working decades ago. Building a solar gravitational lens telescope would require mission durations measured in generations. propulsion systems not yet invented, and instruments capable of maintaining alignment to micro-arc-second precision across interstellar distances. But the principle remains sound, demonstrated by the 1919 eclipse and confirmed by thousands of subsequent observations. Massive objects bend light. The bending creates magnification, distortion, sometimes multiple images. The universe provides natural examples at every scale, from planets and stars up through galaxies and galaxy clusters to the largest gravitationally bound structures known. Fritz Zwicky predicts in 1937 that galaxies could lens more distant galaxies, creating detectable distortions. His prediction waits 4 decades for confirmation, until 1979, when astronomers identify the twin quasar, 2 images of the same quasar separated by 6 arc-seconds, created by a foreground galaxy's gravitational field. The discovery inaugurates an era of gravitational lens astronomy, with catalogues growing to include thousands of lensed quasars, hundreds of lensed galaxies, and countless weaker distortions detected through statistical analysis of cosmic background radiation. The strongest lenses are galaxy clusters, assemblages of hundreds or thousands of galaxies bound together by gravity and embedded in vast halos of dark matter. These clusters mass a quadrillion times more than the Sun, and their gravitational fields create spectacular optical effects, giant arcs of lensed background galaxies, multiple images arranged in symmetric patterns, Einstein rings where alignment approaches perfection. The Hubble Space Telescope captures these distortions routinely, and astronomers use them to map dark matter distribution and to study galaxies otherwise too faint and distant to observe. Moving down the mass scale, individual galaxies also create lensing. The effects are subtler, slight elongations of background galaxy shapes, preferential alignment patterns called weak lensing, but detectable through careful statistical analysis of thousands of background objects. Surveys like the Dark Energy Survey and upcoming projects like the Vera Rubin Observatory will measure billions of galaxy shapes, extracting lensing signals to constrain cosmological parameters and test gravity on cosmic scales. Stars create microlensing events when they pass in front of more distant stars, temporarily brightening them through gravitational focusing. These events are brief hours to months, but distinctive enough to identify automatically in survey data. The optical gravitational lensing experiment monitors hundreds of millions of stars in the galactic bulge, detecting thousands of microlensing events annually and using them to find planets and map stellar populations. Below stellar masses, the detectability drops sharply. Brown dwarfs, failed stars too small to sustain hydrogen fusion, can theoretically create microlensing events, but their scarcity and low mass make detections rare. Planets have been found through microlensing, but only when they orbit stars that themselves are lensing more distant stars, creating brief, additional peaks in the light curve. Free-floating planets, worlds drifting through the galaxy unbound to any star, might create extremely brief microlensing events lasting hours or even minutes. But confirming their planetary nature requires luck and sophisticated follow-up. And then there are smaller objects, still asteroids, comets, interstellar visitors like 3I Atlas. Their masses fall far below what produces detectable lensing under normal circumstances. The deflection angles become sub-micro arc-second. The magnification factors approach, but never exceed 1 plus epsilon, where epsilon is vanishingly small. The Einstein radius shrinks to nano-arc-seconds, requiring alignments so precise that random chance would need billions of years to produce one. Yet, the same physics applies. 3I Atlas curves space-time, bends light, creates in principle all the same effects that galaxy clusters do in practice. The mathematics doesn't distinguish between large and small masses, only between strong and weak fields. Einstein's equations describe both equally well, predicting deflections and magnifications that differ only in magnitude, not in kind. The question becomes whether magnitude matters, whether an effect too small to measure still counts as real, whether 3I Atlas, moving through its curved trajectory under the sun's gravity, simultaneously creates its own tiny curvature that redirects photons by amounts no instrument will ever detect. The answer from physics is yes, the effect exists. The answer from astronomy is no, the effect doesn't matter. Both answers are correct, separated only by whether one cares about principle or practice. Only took 4 years for Einstein to develop general relativity from its initial insights. Only took 4 more for someone to test it with an eclipse. Only took a century more to make gravitational lensing into routine astronomy. And here, now, someone asks whether a small interstellar object might lens background stars, might create detectable distortions, might add one more entry to the catalogue of cosmic optical phenomena. The question itself is beautiful, regardless of its answer. At a distance of 5 billion light-years, a galaxy cluster called Abell 2218 distorts the sky behind it. The cluster contains hundreds of individual galaxies, each a collection of hundreds of billions of stars, all bound together by gravity into a structure measuring millions of light-years across. But the galaxies themselves contribute only a fraction of the cluster's total mass. Most of the mass exists as dark matter invisible, detectable only through its gravitational effects, distributed in a diffuse halo that extends far beyond the visible galaxies. This dark matter halo curves space-time dramatically. Light from galaxies billions of light-years beyond Abell 2218 follows geodesics through this curved region, bending around the cluster in patterns determined by the mass distribution. Some light rays converge, creating magnified images. Others diverge or miss Earth entirely. The resulting view, captured by the Hubble Space Telescope, shows the cluster surrounded by arcs curved, stretched images of background galaxies, some magnified by factors of 10 or more, revealing structures that would otherwise remain invisible. The arcs arrange themselves in patterns predictable from the mass distribution. Gravitational lensing obeys strict geometric rules. For a spherically symmetric lens, background objects form rings or arcs centered on the lens mass. For asymmetric lenses, the patterns become more complex, multiple images at different positions, arcs with varying curvature, distortions that encode information about how mass is distributed in 3 dimensions. Astronomers use these patterns to map dark matter. The visible galaxies in Abell 2218 trace only the luminous material, showing where stars have formed and continue to shine. But the lensing patterns reveal where all the mass resides, dark and luminous combined. By measuring the positions and shapes of lensed background galaxies, researchers can reconstruct the cluster's total mass distribution, determining how dark matter is distributed and how it relates to the visible components. The technique is powerful because it measures mass directly, without assumptions about the relationship between light and matter. Other methods measuring galaxy velocities within the cluster. Observing X-ray emission from hot intracluster gas require assumptions about equilibrium states or temperature distributions. Lensing depends only on geometry and Einstein's field equations. The mass is there or it isn't. The light bends or it doesn't. Some background galaxies behind Abell 2218 appear multiple times, their light taking different paths around the cluster to reach Earth. One galaxy might produce 2 images, or 4, or even more, depending on the alignment and the complexity of the lens. Each image shows the same galaxy at the same moment in cosmic time, but the light paths have different lengths. Photons taking the longer path arrive later, creating a time delay between images that can range from days to years. These time delays serve as cosmic laboratories for testing general relativity and measuring cosmological parameters. When a distant quasar varies in brightness, a flare in its accretion disk, a change in its jet, the variation appears in each lensed image at different times. By measuring these time delays precisely and modeling the lens mass distribution, astronomers can determine the Hubble constant, the rate at which the universe expands. Different research groups using different lensed quasars obtain values that sometimes disagree with other measurement methods, a tension that hints at either unknown systematic errors or new physics beyond standard cosmology. The strongest lensing occurs for the most massive clusters, but even individual galaxies create detectable effects. The Sloan Lens ACS survey identifies hundreds of galaxy-scale lenses, systems where a foreground galaxy at perhaps 2 billion light-years creates arcs or multiple images of background galaxies at 5 or 6 billion light-years. These lenses are smaller, fainter, harder to find, but valuable for studying galaxy mass distributions and dark matter halos around individual galaxies rather than clusters. Weak lensing extends the technique to subtler regimes. Rather than creating obvious arcs or multiple images, weak lensing slightly stretches background galaxies, introducing small shape distortions correlated with the foreground mass distribution. Any individual galaxy's shape tells you nothing. Galaxies have intrinsic shapes that vary randomly. But by averaging over thousands of background galaxies, the correlated distortions emerge from the noise, revealing the presence of mass between observer and sources. This weak lensing signal allows mapping of dark matter on the largest cosmic scales. Surveys observe millions of galaxies, measure their shapes, and correlate those shapes with positions to build maps of where mass concentrates in the universe. These maps show dark matter filaments connecting galaxy clusters, voids where mass density falls below average, and the cosmic web structure predicted by simulations of structure formation. The technique even works with the cosmic microwave background, the ancient light from 380,000 years after the Big Bang. Photons from the CMB have traveled 13 billion years to reach us, passing through all intervening cosmic structure. Their paths have been deflected slightly by every mass concentration they've encountered, creating a cumulative lensing effect that distorts the CMB's temperature and polarization patterns. By analyzing these distortions, cosmologists map the total matter distribution integrated along the line of sight, providing independent confirmation of structure formation models. Moving back down in scale, microlensing by stars creates brightening events rather than resolved images. The lensing star and the background star are too far apart, the angular scales too small, for telescopes to resolve them separately. What's observed instead is the combined light from both stars, with the background star's light temporarily magnified when alignment becomes sufficiently close. The magnification factor can reach hundreds for perfect alignments, making otherwise invisible distant stars detectable for brief periods. Ground-based surveys discover thousands of these events by monitoring dense star fields, the galactic bulge, the Magellanic Clouds, the Andromeda Galaxy. Each event produces a characteristic light curve, rising and falling smoothly over timescales determined by the lens mass and relative velocity. Symmetric curves indicate simple stellar lenses. Asymmetric curves with additional bumps suggest planets orbiting the lensing star, their gravity creating extra magnification when they pass near the Einstein ring. This microlensing planet detection method reaches planets that other techniques miss worlds far from their stars, beyond the reach of radial velocity or transit methods. It finds ice giants at Jupiter distances, super-Earths in outer planetary systems, even free-floating planets drifting unbound through the galaxy. Each detection adds to the census of planetary systems, revealing the diversity of architectures that planet formation produces. But there's a lower mass limit to detectability, set by Einstein radius geometry and photometric precision. For a solar mass lens at galactic bulge distances, the Einstein radius measures a few milliarc seconds, and typical event durations run 20 to 50 days. For a Jupiter mass lens, the Einstein radius shrinks proportionally and event durations drop to days or hours. For an Earth mass lens, you're looking at hours or minutes. For asteroid masses, the events become so brief and so faint that they vanish into the noise of stellar variability and instrumental limitations. 3i Atlas, masses far less than Earth, perhaps comparable to a large asteroid or small moon. Its Einstein radius, calculated for background stars at galactic distances, measures femtoarc seconds quadrillionths of a degree. The timescale for such an event, given the object's velocity relative to background stars, would be seconds or less. The magnification factor, even for a perfect alignment, would barely exceed 1. The probability of alignment precise enough to create any detectable effect approaches 0 with so many decimal places that writing them becomes pointless. Still, galaxy clusters show that scale matters. Arbel 2218 creates spectacular lensing effects not because its individual galaxies are special, but because it gathers enough mass into one region to curve space-time dramatically. If you could gather enough 3i Atlas-sized objects together, billions of them, trillions their combined gravitational field would eventually create detectable lensing. The physics scales linearly with mass. Nature simply hasn't arranged small objects into the necessary concentrations. Only took billions of years for galaxy clusters to assemble from initial density fluctuations. Only took a few 100 million more for astronomers to evolve and build telescopes capable of observing them. And now, those telescopes reveal cosmic magnification effects, natural telescopes formed by gravity itself, allowing glimpses of the universe's most distant structures. Meanwhile, a single small object drifts through our solar system, its gravitational influence too weak to bend even one photon's path by measurable amounts. The mass of 3i Atlas remains uncertain, constrained only by indirect estimates. Astronomers observe its brightness, the amount of sunlight it reflects back toward Earth, and from that brightness they infer its size. Assuming some value for albedo, the fraction of incident light that reflects rather than absorbs. If the object's surface is dark like a carbonaceous asteroid, reflecting perhaps 4% of sunlight, the observed brightness suggests a diameter near 2 kilometers. If brighter, the diameter shrinks proportionally. If darker still, it grows. Volume follows from diameter through simple geometry. Assuming a spherical or near-spherical shape, a 2-kilometer sphere contains roughly 4 cubic kilometers of material. Density remains the largest uncertainty. Icy bodies like comets might have densities around 500 kilograms per cubic meter, roughly half the density of water ice, the rest being void space and porous structure. Rocky asteroids reach 2,000 to 3,000 kilograms per cubic meter. Metallic cores from shattered planets could exceed 7,000 kilograms per cubic meter, though such objects are rare and unlikely for an interstellar visitor. Taking a middle estimate 2 kilometers diameter, 1,000 kilograms per cubic meter density yields a mass near 4 trillion kilograms. That's 4 times 10 to the 12th kilograms, a number large enough that human intuition fails to grasp it. For comparison, The Great Pyramid of Giza masses about 6 billion kilograms. 3I Atlas contains roughly 700 pyramids worth of material, drifting through space at velocities that would cross Earth's diameter in minutes. But by cosmic standards, 4 trillion kilograms is negligible. Earth masses 6 trillion kilograms, a million billion times more massive than the interstellar visitor. The Sun masses 2,000 trillion kilograms, 500,000 billion times more massive still. Even the Moon, a relatively small celestial body, exceeds 3I Atlas by a factor of nearly 20 trillion. The object registers as barely more than dust on cosmic scales, a grain of sand in an ocean of gravitational influence. Gravitational lensing strength scales directly with mass. Double the mass, double the deflection angle for any given geometry. This linear relationship means that 3I Atlas, with a million billionth the mass of Earth, creates deflections a million billionth as strong as Earth would under identical circumstances, and Earth itself, if placed at interstellar distances, would create deflections too small to detect with current instruments. The deflection angle formula makes this explicit. For a point mass, the angle equals 4 times Newton's gravitational constant times the lens mass, divided by the speed of light squared times the impact parameter, the perpendicular distance between the light ray and the lens center. Inserting values for 3I Atlas gravitational constant is 6.67 times 10 to the minus 11 in SI units. Mass is 4 trillion kilograms. Speed of light is 300,000 kilometers per second. Impact parameter perhaps 100 kilometers for a very close pass. The calculation produces an angle near 10 to the minus 14 radians. Converting to arcseconds, a more familiar astronomical unit, where 3,600 arcseconds equal 1 degree, yields roughly 2 millionths of an arcsecond. The best astronomical instruments achieve precision around 10 micro-arcseconds for specific astrometric purposes, making them a factor of 200 too crude to detect 3I Atlas's deflection, even if everything else were perfect, and everything else is never perfect. Atmospheric turbulence blurs star positions by roughly 1 arcsecond from ground-based observatories, though adaptive optics and interferometry can partially compensate. Instrumental systematics, optical distortions, detector imperfections. Tracking errors introduce uncertainties at the milliarcsecond level even from space-based platforms. The Gaia spacecraft achieves micro-arcsecond astrometry only by observing each star dozens of times over years, averaging away random errors to reveal the tiny proper motions and parallaxes that encode stellar distances and velocities. For a single observation of a star during 3I Atlas's passage, none of these sophisticated techniques help. The deflection would appear as a one-time position shift, impossible to distinguish from measurement noise. You can't average over time because the object is moving. By the time you take a second measurement, the geometry has changed. You can't compare to previous observations unless those observations were taken with identical instruments under identical conditions. And even then, unmodeled systematics could easily produce apparent position shifts larger than the lensing effect. The Einstein radius provides another perspective on detectability. This characteristic angular scale, defined as the square root of 4 times gravitational constant times mass times lens source distance difference, divided by speed of light, squared times observer lens distance times observer source distance, determines the region within which lensing effects become significant. For stellar microlensing in our galaxy, Einstein radii typically measure milliarcseconds, creating resolvable arcs or multiple images with current technology. For 3I Atlas lensing background stars, with the object at 5 astronomical units from Earth and background stars at kiloparsec distances, The Einstein radius calculates to roughly 10 nanoarc seconds, billionths of an arc second. This is smaller than the wavelength of visible light by a factor of 1,000,000. No conceivable optical system could resolve features on this angular scale. The quantum nature of light itself prevents it. Magnification offers another potential observable. Even without resolving position shifts, you might detect temporary brightening if a background star passes within a few Einstein radii of 3I Atlas. The magnification factor for a source at angular separation theta from the lens is given by a formula involving the Einstein radius, theta siad magnification, equals theta squared plus 2 times theta psi squared divided by theta times square root of theta squared plus 4 times theta a squared. For theta, much larger than theta, e, the typical case magnification approaches 1. The star's brightness doesn't change detectably. For theta, comparable to theta, e, magnification can reach 2, 3, or higher. For theta, much smaller than theta, e, approaching perfect alignment. Magnification can reach hundreds or thousands. But achieving theta comparable to theta, e, for 3I Atlas, requires angular alignments better than 10 nanoarc seconds. The probability of such alignment, given random stellar positions and the object's trajectory, is approximately the Einstein radius squared, divided by the square of the typical angular separation between stars. In dense star fields, like the galactic bulge, stars are separated by a few arc seconds typically. In the sparse regions where 3I Atlas moves through outer solar system, background stars seen through Earth's atmosphere are separated by arc minutes. The ratio of 10 nanoarc seconds to 60 arc seconds, 1 arc minute equals roughly 10 to the minus 10th. Square that for a two-dimensional probability, and you get 10 to the minus 20th. That's 1 chance in 100 billion. If 3I Atlas passed in front of 1 trillion stars during its passage through the inner solar system, the probability of even one producing a detectable microlensing event would be roughly 1 in 100,000. And the object doesn't pass in front of 1 trillion stars. It passes in front of perhaps a few thousand visible background stars, depending on how faint you're willing to observe. So the scale problem presents itself with mathematical clarity. The mass is too small by factors of millions. The Einstein radius is too small by factors of billions. The alignment probability is too small by factors incomprehensible except in exponential notation. Every relevant parameter falls short of detectability by margins so vast that calling it impossible becomes not pessimism, but precision. Yet the effect exists. 3E Atlas does curve spacetime. Photons passing near it do follow geodesics through that curvature. The deflections are real in the sense that general relativity predicts them with the same equations that accurately describe deflections by the Sun or galaxy clusters. Physics doesn't distinguish between detectable and undetectable effects. That distinction arises only when humans attempt measurements. Only took a century to progress from detecting lensing by the Sun to detecting it by galaxy clusters, to detecting it by individual stars, to attempting detection by planets. Only took another few decades to push precision down to micro-arc second levels, revealing cosmic structure through subtle gravitational distortions. And still, a small interstellar object remains beyond reach, its lensing signature buried beneath instrumental noise and geometric improbability, real but invisible, present but unmeasurable. Astrometry is the measurement of stellar positions. The discipline stretches back centuries, to Hipparchus cataloguing star positions in ancient Greece, to Tycho Brahe's precise naked-eye observations before telescopes existed, to Bradley discovering stellar aberration through careful tracking of Gamma Draconis. Every improvement in precision reveals new phenomena, parallax proving stellar distances, proper motions showing stars' velocities through the galaxy, tiny wobbles indicating unseen planetary companions. Modern astrometry reaches precision levels ancient astronomers couldn't have imagined. The Gaia spacecraft, launched in 2013, measures positions of nearly 2 billion stars with accuracies approaching micro-arc seconds for the brightest objects. It accomplishes this through continuous scanning. The spacecraft rotates slowly, sweeping its 2 telescopes across the sky, measuring each star's position dozens of times over years. The repeated observations average away random errors, while careful modeling removes systematic effects from spacecraft motion, optical distortions, and relativistic corrections. From Earth's surface, astrometric precision faces harsher limits. Atmospheric turbulence blurs star images, making them appear to dance and shimmer. Adaptive optics systems can partially compensate, using deformable mirrors to correct wavefront distortions in real time. But the corrections are imperfect and limited to small patches of sky. Long exposure photography reduces random atmospheric errors through time averaging, but introduces other complications: Earth's rotation during exposure, tracking imperfections, differential atmospheric refraction affecting stars at different elevations. Still, ground-based astrometry serves important purposes. Tracking asteroids and comets requires knowing their positions precisely to calculate orbits and predict future locations. Near-Earth objects that might pose collision hazards need positions accurate to fractions of an arc-second to determine whether their paths intersect Earth's orbit years or decades hence. And for the brightest stars, ground-based observations can achieve milli-arc-second precision when conditions are favorable and observers are careful. For 3i Atlas, multiple observatories track its motion through the sky. Each night of observation adds new position measurements, refining the orbit calculation, narrowing uncertainty about where the object came from and where it's going. The positions are referenced to background stars. The object appears to move while stars remain fixed, allowing precise determination of the object's trajectory relative to the distant stellar background. But those background stars are not actually fixed. They possess their own proper motions, apparent movements across the sky caused by their velocities through the galaxy relative to the Sun. Bright nearby stars move fastest, their proper motions measured in tens or hundreds of milliarc seconds per year. Distant stars move more slowly, but even they shift position over years and decades. To use them as reference points, their proper motions must be known and corrected for. This is where Gaia's catalog becomes invaluable. It provides not just current positions but also proper motions, parallaxes, and radial velocities for hundreds of millions of stars. An observer can download the catalog data for any patch of sky, calculate where stars should appear at any given time, and use those predicted positions as a fixed reference frame. Deviations from predicted positions then indicate either measurement errors or real phenomena, gravitational lensing, undiscovered binary companions, planets, or instrumental problems. If 3i Atlas were massive enough to lens background stars detectably, the signature would appear in these astrometric residuals. Stars near the object's path would show small position shifts, appearing slightly displaced from their catalog positions in directions radially outward from 3i Atlas's location. The pattern would be systematic and geometric, following predictions from lensing theory. As the object moved across the sky, different stars would show deflections while previously affected stars returned to normal positions. Searching for such signals requires careful analysis. First, observe a field containing the object and dozens or hundreds of background stars. Measure each star's position with the best precision available, perhaps tens of milliarc-seconds from ground-based images, better from space-based observations. Second, compare measured positions to Gaia catalog predictions, accounting for proper motion and parallax. Third, look for correlated residuals. Do stars near 3i Atlas show systematic shifts? The challenge is separating signal from noise. Every observation contains errors. Random photon noise limits centroid measurements, especially for faint stars. Atmospheric turbulence adds scatter. Detector defects create spurious signals. Optical distortions shift apparent positions systematically across the field. Any of these effects could produce apparent position shifts that mimic or mask lensing signatures. Statistical techniques help. By observing many stars simultaneously, random errors average away while systematic signals strengthen. If lensing is present, stars near the object should show deflections while stars far from it should not. The pattern should match theoretical predictions for the object's estimated mass and geometry. If the pattern appears random or doesn't match lensing predictions, it's likely instrumental or atmospheric effects rather than real gravitational deflection. But for 3i Atlas, the expected deflection is 2/millionths of an arc-second, far below the noise level of any practical observation. Even if you observed 1,000 stars simultaneously with perfect instruments, the random errors would be tens of thousands of times larger than the signal. No statistical technique can extract signal that deeply buried in noise. It's not a matter of observing longer or harder. The signal is simply too weak compared to fundamental limitations. Differential astrometry offers slight improvement. Rather than measuring absolute positions, measure the relative positions between stars very close together on the sky, many systematic errors, atmospheric effects, telescope tracking. Some optical distortions affect nearby stars similarly and cancel when taking differences. For binary stars separated by arc-seconds, differential astrometry can reach micro-arc-second precision over long baselines. Could this work for lensing detection? In principle, if 3i Atlas passed directly between two stars separated by small angles, one star would be deflected while the other wasn't, and the change in their relative separation might be detectable even if absolute position shifts were not. In practice, the geometry rarely cooperates. Most stars are separated by arc minutes or more, too large for effective differential measurements, and even when closer pairs exist, the probability that 3i Atlas passes between them with the right geometry remains vanishingly small. Interferometry provides another path to high precision. By combining light from multiple telescopes separated by large distances, astronomers create an effective aperture much larger than any single telescope, achieving angular resolution proportional to the baseline separation. Very long baseline interferometry using radio telescopes separated by thousands of kilometers reaches micro-arc-second resolution. Routinely, optical interferometry, more challenging due to shorter wavelengths and atmospheric turbulence, still achieves milliarc-second resolution for bright sources. But interferometry measures visibility functions and closure phases, not simple positions. Converting these measurements to astrometric positions requires careful modeling and assumptions about source structure. For point sources like stars, the technique works well. For extended or resolved sources, interpretation becomes complex. And for detecting tiny deflections in star positions, you face the same fundamental problem: the signal is too small compared to measurement uncertainties. Some proposals suggest using pulsar timing instead. Pulsars emit radio pulses with extraordinary regularity, effectively serving as natural clocks scattered throughout the galaxy. By monitoring pulse arrival times with nanosecond precision, astronomers detect gravitational waves, measure interstellar medium properties, and test general relativity in strong field regimes. Could pulsar timing detect gravitational lensing by small objects? In theory, yes. If a massive object passed between Earth and a pulsar, the gravitational time delay, the Shapiro delay, would cause pulses to arrive slightly late, then return to normal as the object moved away. The effect scales with mass and, inversely, with impact parameter. For solar mass objects at astronomical unit distances, delays could reach microseconds, detectable with current timing precision. For 3I Atlas, the delay calculates to femtoseconds, millionths of a nanosecond, far below timing precision, and the geometric probability remains unfavorable. Few pulsars are positioned such that 3I Atlas's trajectory passes close to the line of sight. The technique that works for stellar mass objects and reveals gravitational waves from merging black holes cannot detect interstellar visitors massing mere trillions of kilograms, and so the object moves through space, its position tracked nightly by automated surveys, its trajectory refined with each observation. The astrometry reveals where it's been and where it's going, confirms its interstellar origin, constrains its mass through non-gravitational acceleration signatures. But the astrometry cannot, will not, reveal gravitational deflections of background starlight, because those deflections exist only in the equations, buried beneath noise by factors too large to overcome with any realistic observation. Only took centuries to progress from measuring star positions to the nearest arc minute to measuring them to micro-arc seconds. Only took decades more to apply those measurements to detecting planets, asteroids, gravitational waves, relativistic effects, and still, some effects remain too small, some masses too insignificant, some signals too deeply buried. The universe sets limits, and instruments reach toward them asymptotically, never quite arriving. Beyond Neptune's orbit, beyond the scattered disk where Pluto and Eris trace their elliptical paths, lies a region so vast and dark that it contains most of the solar system's volume, yet almost none of its known mass. The Oort cloud stretches from perhaps 2,000 astronomical units outward to 100,000 AU or more, halfway to the nearest stars, far enough that the sun appears as merely the brightest point in a sky full of stars, far enough that orbital periods measure in millions of years. No telescope has directly observed an Oort cloud object in its native environment. The region is simply too distant, the objects too small and dark, reflecting too little sunlight across too much space for detection. What astronomers know about the Oort cloud comes from inference from long-period comets that fall inward toward the sun. Their orbits traced back to aphelion distances in the outer cloud, their compositions analyzed as they sublimate and release dust and gas under solar heating. These comets arrive from random directions, their orbital planes scattered across all angles rather than concentrated in the ecliptic like planets and asteroids. This isotropy suggests the Oort cloud forms a spherical shell rather than a disk, surrounding the solar system equally in all directions. The long orbital periods, thousands to millions of years, and the large aphelion distances indicate these objects spend most of their existence in the outer darkness, only briefly passing through the inner solar system where they become visible. Estimates of the Oort cloud's population vary wildly. Perhaps 1 trillion objects larger than 1 kilometer diameter, perhaps 10 times that number, perhaps fewer. The uncertainty reflects the impossibility of direct observation and the small sample size of observable comets. Every few years, another long-period comet appears, brightens, develops a tail, then fades as it rounds the sun and returns to the outer darkness. From these rare visitors, astronomers attempt to infer the properties of a population that will never be fully catalogued, The total mass of the Oort cloud remains similarly uncertain. Individual comets mass perhaps 1 trillion kilograms each, similar to 3I Atlas. Small by solar system standards, but substantial compared to human scales. 1 trillion such objects would total 10 to the 24 kilograms, roughly the mass of Earth, but spread across a volume with radius 100,000 AU. The density becomes absurdly low. Individual objects separated by millions of kilometers, drifting in orbits so slow that their positions barely change over human lifetimes. These objects formed elsewhere, most likely in the region between Jupiter and Neptune, where ice could condense, but gravitational interactions with giant planets eventually scattered debris outward. Some fragments fell inward to collide with terrestrial planets. Some escaped the solar system entirely. Becoming interstellar wanderers like 3I Atlas presumably became from some other star's planetary system. Others reached the outer extremes of the Sun's gravitational influence, settling into enormous orbits that barely bind them against galactic tides and passing stars. The Oort cloud is not gravitationally isolated. Nearby stars passing within a few light-years exert tidal forces that perturb cloud objects, sometimes dislodging them inward where they become observable comets. The galactic tide, the difference in the Milky Way's gravitational field across the cloud's diameter, creates similar perturbations. Giant molecular clouds, regions of dense interstellar gas where stars form, occasionally pass near the solar system and disturb the cloud. All these external influences shake the Oort cloud gently but persistently, sending a slow rain of comets inward over geological time. Other stars likely have their own Oort clouds, though none have been detected. Every planetary system should generate scattered debris during formation, and some fraction of that debris should settle into distant orbits rather than escaping entirely. The galaxy presumably contains countless such clouds, overlapping spheres of icy debris surrounding every star that has planets, each cloud invisible until some perturbation sends an object inward where it might cross another star's field of view. This raises the question of where 3I Atlas originated. Did it form in another star's planetary system, get scattered outward into that star's Oort cloud, then get perturbed again millions of years later to escape into interstellar space? Or did it escape directly during the early chaotic phase of its birth system, never settling into a long-period orbit? The hyperbolic trajectory and high velocity suggest a recent ejection event, but recent in astronomical terms could mean any time in the past million years. The object's composition offers clues. Spectroscopy reveals absorption features indicating water ice, perhaps mixed with organic compounds, materials expected from formation in the outer regions of a planetary system where temperatures allow volatile ices to condense. The dark surface suggests radiation processing, the slow alteration of surface chemistry by cosmic rays and ultraviolet light over eons. Similar darkening appears on solar system comets and outer asteroids, evidence of vast time spent in cold darkness. If 3I Atlas spent millions of years in interstellar space between stars, it would have experienced this radiation processing without interruption. No stellar wind to ablate its surface, no solar heating to drive sublimation, just slow bombardment by cosmic rays and the occasional impact by interstellar dust particles traveling at tens of kilometers per second. The surface would develop a lag of radiation-darkened material, insulating whatever pristine ice might remain beneath. The velocity provides additional context. The object moves relative to the local standard of rest, the average velocity of stars in the solar neighborhood, at roughly 30 kilometers per second. This is typical for stars in the galactic disk, suggesting 3I Atlas comes from a nearby system, within perhaps tens of light years. At such velocities, it would take millions of years to cross even this small galactic neighborhood, time enough for surfaces to darken and for its origin system to move elsewhere through galactic rotation. Other interstellar visitors will come, eventually. Oumuamua in 2017 proved they exist. 2I Borisov in 2019 provided a second example. This one more comet-like with visible outgassing and a clear coma. 3U Atlas in 2025 adds a third data point. The detection rate suggests 1 or 2 interstellar objects per year pass through the inner solar system within Jupiter's orbit, with many more passing undetected in the outer system or arriving too faint for current surveys to notice. As telescopes improve, as survey systems like the Vera Rubin Observatory begin operations, scanning the entire sky repeatedly to detect anything that moves or changes, the detection rate will increase. Perhaps dozens of interstellar visitors per year will be found, each one carrying information about planetary system formation elsewhere, about the efficiency of scattering processes, about the composition of materials in other stellar environments. Each visitor will be small, dark, fast-moving. Each will curve space-time by infinitesimal amounts. Each will create gravitational deflections far too small to measure, Einstein rings far too small to resolve, microlensing events far too brief and faint to detect. The Oort cloud objects do the same trillions of small masses drifting in darkness, each one a negligible gravitational presence, collectively significant only in their abundance and their occasional ability to fall inward and become comets. The galaxy is full of such objects, debris from planetary formation scattered across interstellar space. They outnumber stars by vast factors, yet contribute almost nothing to the galaxy's total mass. Dark matter, the invisible mass that dominates galactic dynamics, does not consist of interstellar visitors or Oort cloud objects. It's something else entirely. Something that doesn't interact with light even weakly. Something that can only be detected through its gravitational effects on larger scales. But the small, icy bodies exist in their own right, independent of cosmological significance. They orbit slowly in the darkness, or drift between stars, or occasionally plunge sunward to blaze briefly as comets. They carry the solar system's formation history in their compositions, preserve pristine ice from the molecular cloud that collapsed to form the sun, record impacts and radiation damage from billions of years in deep space, and they curve space-time microscopically, immeasurably, according to the same equations that describe quasars and galaxy clusters and the universe itself. Only took 4.5 billion years for the Oort cloud to accumulate. Only took a few million more for astronomers to infer its existence from comet orbits. And now they watch for interstellar visitors, objects from other stars' Oort clouds or scattered disks, measuring their trajectories and compositions and wondering whether these visitors might create detectable gravitational effects. The answer, as always, depends on scale, and the scale remains wrong by many orders of magnitude. The first interstellar visitor enters the astronomical record on October 19, 2017, when the Pan-STARRS telescope in Hawaii detects an object moving rapidly through the inner solar system. The trajectory appears unusual, immediately hyperbolic rather than elliptical, the object moving too fast to be gravitationally bound to the sun. Initial observations suggest a comet, perhaps a long-period one from the Oort cloud, but no coma appears, no tail develops, no outgassing signature emerges even as the object approaches perihelion. Within weeks, enough observations accumulate to establish the orbit definitively. The eccentricity exceeds a hyperbolic trajectory that entered from interstellar space, swung around the sun, and departed back into the void. The object had already passed perihelion before discovery, already begun its outward journey, visible only because it happened to pass relatively close to Earth on its way out. By the time astronomers recognize its significance, it's already fading, receding beyond the reach of detailed observation. They name it Oumuamua, a Hawaiian word meaning scout or messenger, honoring the telescope that found it. The designation, One-Eye Oumuamua, establishes the nomenclature for interstellar objects, the eye distinguishing them from comets and asteroids, the number indicating discovery order. It measures perhaps 100 to 400 meters along its longest axis, though the size remains uncertain given the unknown albedo and the object's extreme elongation. That elongation, at least 5 to 1 length to width ratio, possibly 10:1 or more, distinguishes Oumuamua from most solar system objects. Asteroids are generally more spherical, their shapes determined by gravitational collapse during formation or by impact erosion over billions of years. The elongated form suggests either a fragment from a larger body, a collision product that never gravitationally relaxed into a sphere, or possibly something formed through processes not common in the solar system. The color appears reddish, similar to organic-rich outer solar system objects, consistent with radiation processing of surface materials over long timescales in interstellar space. Spectroscopy reveals no clear absorption features, no evidence of water ice or specific minerals, just a relatively featureless spectrum that provides few compositional clues. The surface reflects about 10% of incident sunlight, brighter than the darkest asteroids, darker than fresh ice, consistent with irradiated organic material coating an unknown substrate. As observations continue through late 2017, astronomers notice something unexpected. The object's trajectory deviates slightly from a purely gravitational orbit. It accelerates away from the Sun by a small amount beyond what solar gravity alone would produce. The effect is subtle, requiring precise astrometry to detect, but statistically significant. Something other than gravity is affecting Oumuamua's motion. For comets, such non-gravitational accelerations are common and well understood. Sublimating ice creates jets of gas that act as natural rocket engines, pushing the comet in directions determined by rotation and active region distribution. But Oumuamua shows no outgassing, no coma, no spectroscopic evidence of volatile release. Whatever causes the acceleration must be different from normal cometary activity. Multiple explanations emerge. Perhaps the object is outgassing, but the gas production is too low to create a visible coma, or the active region is too small, or the observation geometry is unfavorable. Perhaps radiation pressure photons from the Sun transferring momentum when they reflect or absorb provides the acceleration, which would require the object to have very low density or very high surface area to mass ratio, like a thin sheet or a porous aggregate. Perhaps thermal effects analogous to the Yarkovsky effect for asteroids create asymmetric infrared emission that produces net thrust. The debate continues for years, with papers proposing various natural mechanisms and occasionally more exotic possibilities. Some suggest Oumuamua might be artificial, a light sail or probe from another civilization, though no signals are detected despite searches at various wavelengths. Most astronomers favor natural explanations, though uncertainty remains about which specific mechanism dominates. The object is too faint, too distant, too poorly observed during its brief visibility for definitive answers. What Oumuamua teaches is that interstellar objects exist, that they pass through the solar system occasionally, that they can have unexpected properties differing from familiar comets and asteroids. It establishes that survey telescopes, if sufficiently sensitive and wide field, can detect these visitors despite their faintness and rapid motion. And it reveals how difficult characterization becomes when objects are discovered only after perihelion, when they're already fading and receding. The second interstellar visitor arrives in August 2019. Gennady Borisov, an amateur astronomer operating a telescope in Crimea, discovers a faint comet that subsequent observations reveal to have a hyperbolic orbit. Unlike Oumuamua, this object designated 2I Borisov behaves like a normal comet. It develops a prominent coma, releases gas and dust, shows spectroscopic features consistent with water, carbon monoxide, and other volatiles. It appears less unusual, more familiar, confirming that at least some interstellar objects resemble solar system comets in composition and behavior. The orbit indicates 2I Borisov entered the solar system from a different direction than Oumuamua, suggesting multiple source regions or at least significant randomness in interstellar object trajectories. The object's discovery before perihelion allows extensive follow-up observations as it brightens, reaches closest approach to the Sun, then fades again on its outbound trajectory. Multiple telescopes observe it across wavelengths from radio to ultraviolet, gathering data about composition, outgassing rates, dust properties, nucleus size. The observations reveal that 2I Borisov's composition resembles solar system comets, but with some differences. The ratio of carbon monoxide to water is higher than typical for most solar system comets, though still within the range seen for some Oort cloud objects. This suggests formation in a colder environment or different chemical conditions, consistent with origin in another stellar system where planetary architecture or formation timing might differ from the solar nebula. Both Oumuamua and 2I Borisov are small, hundreds of meters to perhaps a few kilometers in size. Both are dark, reflecting relatively little sunlight. Both move at velocities typical of stars in the local galactic neighborhood, suggesting origins from nearby systems rather than exotic high-velocity sources. And both curve spacetime by amounts utterly negligible for observational purposes. Their mass is too small to create detectable gravitational effects on background starlight or foreground solar system objects. Could either object have lensed background stars during their passage through the solar system? The question receives little attention in the literature. Not because it's uninteresting, but because the answer is obviously no. The masses are too small, the Einstein radii too tiny, the deflection angles too far below measurement thresholds. Researchers focus on what can be learned: composition, orbit, non-gravitational forces, formation environment, rather than on effects that exist only in principle. Still, the question has pedagogical value. It forces explicit calculation of lensing parameters, reveals the quantitative gulf between detectable and undetectable effects, illustrates why certain observations are never attempted. For Oumuamua, assuming a mass of perhaps 10 trillion kilograms based on size and density estimates, the Einstein radius for background stars at kiloparsec distances calculates to tens of femtoarc seconds. The deflection angle for close passes is microarc seconds at best, undetectable by thousands of times the margin. The detection rate of 1 or 2 interstellar objects per year suggests the local galactic neighborhood contains a substantial reservoir of such objects. If every star contributes debris to interstellar space during planetary formation, and if ejection processes are reasonably efficient, the space between stars might contain interstellar objects outnumbering stars themselves by factors of millions or billions. Most would never be detected, drifting invisibly through the dark, only occasionally passing close enough to the Sun to reflect sufficient light for discovery. Future surveys will find more. The Vera Rubin Observatory, when operational, will scan the entire visible sky every few nights to unprecedented depth, detecting objects much fainter than current surveys reach. Estimates suggest it might find dozens to hundreds of interstellar visitors per year, enough to establish statistical property size distributions, compositional variations, velocity dispersions, arrival directions, Each discovery will add to the catalog of objects too small to lens background stars, too faint to study in detail, but valuable nonetheless for what they reveal about planetary system formation elsewhere. And 3i Atlas continues this tradition. It resembles Oumuamua in showing no clear outgassing, though it's larger. It differs from 2i Borisov in lacking a coma, though observations remain ongoing and activity could develop as it approaches perihelion. It moves through the outer solar system where cold temperatures might suppress volatile release, where solar heating is too weak to drive vigorous sublimation. Its trajectory curves under the sun's gravity, hyperbolic but not wildly so, suggesting an origin velocity relative to nearby stars of perhaps 20 or 30 kilometers per second. Its mass remains uncertain within factors of several. Its composition unknown beyond generic surface properties. Its rotation and shape poorly constrained. What is certain is that it curves space-time by amounts no telescope will measure, creates lensing effects no observation will detect, bends light by angles that exist mathematically but remain forever hidden beneath the noise of quantum uncertainty and instrumental limitation. The universe contains effects at every scale, but only some scales permit observation. And 3i Atlas operates below that threshold in its gravitational influence even as it moves visibly through the sky. Only took 2 years between the first and second interstellar object discoveries. Only took 6 more for the third. The rate is increasing as surveys improve, as detection algorithms optimize, as astronomers learn what to look for. And each object teaches something about compositions, trajectories, non-gravitational forces, while simultaneously demonstrating its gravitational insignificance through the absence of any detectable lensing, time delay, or orbital perturbation on other bodies. The lesson repeats mass matters, and small masses matter only when they're not too small. Light carries information. Every photon reaching Earth from 3i Atlas traveled millions of kilometers through space, reflected from the object's surface after being emitted by the sun. That reflection is not neutral. Different materials absorb and reflect different wavelengths preferentially, creating spectral signatures that encode surface composition. By spreading the reflected light into a spectrum, measuring intensity at each wavelength, astronomers can infer what the object is made of without ever touching it. The technique is spectroscopy, fundamental to astronomy since Fraunhofer discovered dark lines in the solar spectrum in 1814. Those lines' absorption features at specific wavelengths correspond to chemical elements in the sun's atmosphere absorbing light at characteristic frequencies determined by quantum mechanics. Each element and molecule has a unique spectral fingerprint, a pattern of lines that appears wherever that substance exists, whether in stellar atmospheres, planetary nebulae, interstellar clouds, or the surfaces of distant objects. For 3i Atlas, spectroscopy begins with collecting enough light to analyze. The object is faint magnitude 20 or dimmer, requiring large telescopes and long exposure times. Even then, the spectrum is weak, dominated by scattered sunlight rather than thermal emission at these cold temperatures. The reflected spectrum will show the sun's spectral features superimposed on any absorption or reflection characteristics from the object's surface. Observers use medium to high-resolution spectrographs, instruments that disperse light into spectra using gratings or prisms. The spectrum spreads across a detector, with each pixel recording intensity at a narrow wavelength range. For visible light spanning 400 to 700 nanometers, a resolution of 1 nanometer provides 300 independent wavelength bins. Higher resolution reveals finer details but requires more light, longer exposures, or larger telescopes. The initial spectra show no dramatic features. The overall color appears slightly red, reflecting more at longer wavelengths than shorter ones, similar to many outer solar system objects. This reddening typically indicates organic compounds, tholins created by radiation processing of ices containing carbon, nitrogen, and other elements. Ultraviolet light and cosmic rays break molecular bonds, allowing atoms to recombine into complex organic molecules that appear dark and reddish across visible and near-infrared wavelengths. Water ice, if present on the surface, would show absorption features near 1.5 and 2.2 microns in the near-infrared. Carbon dioxide ice absorbs strongly at 1.5, 2.0, and 2.7 microns. Methane ice has features at 1.7, 2.3, and 3.3 microns. Different minerals show different absorption patterns. Pyroxenes have broad features near 1 micron. Olivines have sharper features. Silicates show patterns across multiple wavelengths. By comparing observed spectra to laboratory measurements of various materials, astronomers can identify likely surface compositions. For 3I Atlas, the signal-to-noise ratio in the spectrum remains marginal. Some observations suggest weak water ice features, but the detections are not statistically robust. The absorption dips are comparable to noise levels, and different observation epochs show slightly different results. This could indicate genuine variability as the object rotates and different surface regions become visible, or it could simply reflect measurement uncertainties in faint spectra of distant objects. The ambiguity frustrates attempts at definitive characterization. Is the object icy like a comet, rocky like an asteroid, or some mixture? Does it have fresh surface ice, or is everything buried beneath radiation-processed lag? Is the composition uniform, or does it vary across the surface? These questions remain unanswered, awaiting either better observations or closer approaches that might never occur. Polarimetry provides complementary information. Light reflecting from surfaces becomes partially polarized, with the degree and direction of polarization depending on surface properties, particle size, roughness, composition, viewing geometry. Comets typically show low polarization, consistent with fluffy aggregates of small particles. Rocky asteroids show higher polarization. Icy surfaces can show various polarization depending on grain size and contamination. Measurements of 3I Atlas's polarization suggest values intermediate between typical comets and asteroids. But again, uncertainties are large. The object is faint. Polarization measurements require high signal-to-noise, and atmospheric seeing degrades polarimetric precision. Different observers report slightly different values, and modeling the results in terms of surface properties involves numerous assumptions about particle size distributions and mixing ratios. Thermal infrared observations would help constrain size and albedo independently. By measuring how much thermal radiation the object emits at mid-infrared wavelengths, around 10 to 20 microns, where objects at these temperatures radiate most strongly, astronomers can determine the temperature. Combined with distance from the Sun and assumptions about thermal inertia, temperature yields albedo, and albedo combined with brightness yields size. But 3I Atlas is too faint for current infrared facilities at these wavelengths. The James Webb Space Telescope could potentially detect it, but the object's motion creates challenges for observations requiring long integrations. The telescope must track the object's motion against the background sky, and scheduling such observations competes with countless other science programs. As of now, no confirmed JWST observations of 3I Atlas exist in the public archive, even without detailed composition. The general picture emerges from analogy. Interstellar objects likely resemble solar system comets and outer asteroids in composition because they form through similar processes, Condensation from protoplanetary disks in the cold outer regions beyond the snowline where water and other volatiles can freeze. The reddish color, the lack of obvious spectral features, the faintness, all these are consistent with organic rich surfaces similar to what's seen on Kuiper Belt objects and long-period comets. Radiation processing in interstellar space would darken surfaces over time. Cosmic rays, high-energy particles permeating the galaxy impact the surface, breaking chemical bonds and creating radiation damage. The flux is low but persistent, and over millions of years in interstellar transit, surfaces accumulate significant dosage. Laboratory experiments irradiating ice mixtures with energetic particles show that surfaces darken, redden, and develop complex organic molecules, matching observations of various solar system objects. If 3I Atlas spent 10 million years traveling through interstellar space before entering the solar system, its surface would have experienced extensive radiation processing. Any pristine ice would be buried beneath a lag of irradiated material, only if the object develops significant outgassing near perihelion. Removing this lag and exposing fresh ice would the true interior composition become apparent. So far, no such outgassing has been detected, but the object hasn't yet reached perihelion, and temperatures may not be sufficient to drive vigorous sublimation given its current distance from the Sun. The spectrum of reflected light, then, tells a partial story. It reveals surface properties, but not necessarily bulk composition. It shows the effects of radiation and time, but not the original formation conditions. It provides hints and constraints, but not definitive answers. This is typical for spectroscopy of faint, distant objects, informative but incomplete, valuable but frustrating. What spectroscopy cannot reveal is gravitational properties. The composition informs mass estimates through density. Ice is less dense than rock. Rock less dense than metal, but the uncertainties are large and the connection indirect. A purely icy object 2 kilometers in diameter masses perhaps 4 trillion kilograms. A rocky object the same size masses perhaps 10 trillion kilograms. A porous aggregate might be less dense than solid ice. The factor of several uncertainty in mass translates directly to uncertainty in any gravitational effects the object might produce. Not that it matters for lensing. Whether 3I Atlas masses 4 trillion or 10 trillion kilograms, the deflection angles remain sub-micro arcsecond. The Einstein radii remain femto arcsecond. The detectability remains far beyond current capabilities. The composition matters for understanding formation environments and ejection mechanisms, for comparing interstellar objects to solar system bodies, for building models of planetary system evolution. It doesn't matter for gravitational lensing, where the mass is simply too small regardless of its exact value. Light, then, reveals chemistry but not gravity. Photons scattered from the surface encode information about molecular bonds and crystal structures and radiation damage. Photons deflected by the object's gravitational field encode information about space-time curvature and mass distribution. The first category reaches Earth in measurable quantities, allowing spectroscopy. The second category reaches Earth with deflections too small to detect, making lensing impossible. Both are real phenomena. Both follow physical laws, but only one permits observation with current or foreseeable technology. Only took 4 centuries to progress from Galileo's first telescopic observations to modern high-resolution spectroscopy revealing compositions of objects across the solar system. Only took another few decades to extend those techniques to interstellar visitors, inferring their properties from faint reflected light. And still, the gravitational influence remains hidden, calculable but unmeasurable, present but invisible. a reminder that not all physical effects are observable effects. Distance in astronomy is never simple. When observing an object in the sky, its angular position is clear right ascension and declination, coordinates on the celestial sphere. But that angular position alone doesn't reveal how far away the object is. A small, nearby object and a large distant object can appear identical in angular size and brightness. Breaking this degeneracy requires additional measurements, techniques that exploit geometry or physics to extract the third dimension of space. For objects in the solar system, the most direct method is parallax the apparent shift in position when viewed from different locations. Hold a finger at arm's length and close one eye, then the other. The finger appears to jump against the distant background. The amount of jump depends on the spacing between your eyes and the distance to your finger. Larger spacing or closer fingers create larger apparent shifts. Smaller spacing or more distant fingers create smaller shifts. Earth's orbit provides the baseline for parallax measurements of solar system objects. Observe an asteroid in January when Earth is on one side of the Sun. Then again in July when Earth is on the opposite side, 300 million kilometers away. The asteroid appears to shift position against the background stars. Measure that shift precisely. Apply some geometry involving the Earth-Sun distance and the observation angles, and the asteroid's distance emerges from the calculation. For 3i Atlas, parallax measurements proceed continuously as Earth orbits the Sun. Each night's observation provides a position measurement from a slightly different location in space. The object itself is also moving. So separating parallax shift from actual motion requires modeling both effects simultaneously. This is standard astrometric practice fit a model, including the object's position, velocity, acceleration, and parallax to all available observations, minimizing residuals to find the best fit parameters. The observations come from multiple observatories distributed across Earth's surface. This provides additional baselines beyond just Earth's orbital motion. Two telescopes, separated by thousands of kilometers, observe the same object simultaneously from different positions, creating geometric parallax even within a single night. The effect is small for outer solar system objects, milliarc seconds at most, but detectable with careful astrometry. From these measurements, 3i Atlas's distance is determined to be approximately 5.2 astronomical units as of a particular observation date. That's 780 million kilometers, roughly Jupiter's orbital distance, though the object's trajectory doesn't follow Jupiter's orbit. The uncertainty in this distance is perhaps a few million kilometers, small in absolute terms, but large enough to affect calculations of the object's size based on apparent brightness. The distance changes daily as both Earth and 3i Atlas move through space. The object approaches perihelion, its closest point to the Sun, which will occur in several months at a distance of perhaps 3.8 AU. After perihelion, it will recede, moving outward on its hyperbolic trajectory, eventually crossing Neptune's orbit and continuing into the outer solar system and beyond. By the time it reaches the distance where the Oort cloud begins, decades or centuries from now, it will be far too faint for any telescope to detect. Combining distance with apparent brightness yields the object's absolute magnitude, how bright it would appear at a standard distance of 1 AU from both the Sun and Earth. This absolute magnitude, combined with assumptions about albedo, gives size estimates. If the albedo is 10%, the diameter is roughly 2 kilometers. If albedo is 20%, diameter shrinks to about 1.4 kilometers. If albedo is only 5%, diameter grows to nearly 3 kilometers. The uncertainty in albedo translates directly to uncertainty in size, which translates to uncertainty in mass when combined with density assumptions. Radar would remove some of this uncertainty. By bouncing radio waves off the object and measuring the return signal, strength and time delay, astronomers can determine distance with extreme precision meters or even centimeters and obtain crude shape information from the spread in return times as different parts of the surface reflect at slightly different ranges. But 3I Atlas is too distant for planetary radar systems. The Arecibo Observatory, which could detect objects out to several AU under favorable conditions, collapsed in 2020. The Goldstone radar in California has sufficient power but limited sensitivity for targets this far and this faint. So distance relies on optical parallax, less precise than radar but sufficient for orbital calculations. The orbit itself becomes well determined after weeks of observations, with uncertainties shrinking as more data accumulates. The orbital element's semi-major axis, eccentricity, inclination, argument of perihelion, longitude of ascending node, time of perihelion passage are fitted to the observations, with formal uncertainties that account for measurement noise and model limitations. The hyperbolic eccentricity measuring approximately 1.3, meaning 30% excess over the parabolic escape value, indicates the object entered the solar system with significant interstellar velocity. Working backward from the orbit, astronomers calculate the incoming velocity vector at infinity, the direction and speed the object had before the Sun's gravity began significantly affecting its trajectory. This vector points roughly toward a particular region of the sky, suggesting a possible origin direction, though the object could have traveled for millions of years from a system no longer in that direction due to galactic rotation. For gravitational lensing calculations, what matters is the distance to both the lens and the background sources. The lens is 3I Atlas at 5.2 AU, well determined through parallax. The background sources are stars, their distances known from a combination of parallax, spectroscopic parallax, and statistical models. Bright nearby stars have distances measured by Gaia to within a few percent. Faint distant stars have distances uncertain by factors of 2 or more. But for lensing purposes, what matters is that they're vastly more distant than the lens kiloparsecs versus AU, factors of millions in distance ratio. This distance ratio enters the lensing equations critically. The deflection angle and Einstein radius both depend on combinations like distance to source minus distance to lens divided by distance to source times distance to lens. For sources at kiloparsec distances and lenses at AU distances, this ratio is approximately 1 divided by the lens distance, since the source distance is so much larger that subtracting the lens distance changes almost nothing. But the Einstein radius also depends on lens mass, and that dependence is through the square root, double the mass, increase the Einstein radius by square root of 2, about 1.4. Double the distance to the lens, decrease the Einstein radius by square root of 2. The two effects roughly cancel for typical geometries, but not exactly, and both mass and distance have uncertainties that propagate through to uncertainties in predicted lensing effects. Not that uncertainties matter when the effect is undetectable by orders of magnitude. Whether the Einstein radius is 10 femtoarc seconds or 20 femtoarc seconds, it remains far below any conceivable measurement precision. Whether the deflection is 2 microarc seconds or 4 microarc seconds, it remains buried beneath atmospheric and instrumental noise. The parallax measurements that determine distance so precisely for orbital calculations provide no help for lensing detection, because the lensing effect is fundamentally too small. Triangulation works. Humans have used it for millennia to measure distances to inaccessible objects, distant mountains, enemy ships, celestial bodies, The principle scales from surveying terrestrial landscapes to mapping the galaxy's structure. Hipparchus measured distances to the Moon through parallax. Bessel first measured stellar parallax in 1838, revealing that 61 Cygni lies about 11 light-years away. Gaia measures parallax for billions of stars, building a three-dimensional map of the Milky Way. And now, the same technique determines that 3I Atlas is 780 million kilometers away, moving at 15 kilometers per second relative to the Sun, massing perhaps 10 trillion kilograms, give or take a factor of several. These numbers are known. They're uncertain, but constrained. They enter calculations of gravitational effects and produce predictions that affirm the object will not produce detectable lensing. The distance is right. The mass is right. The geometry is right. The predictions are reliable. And the predictions say nothing will be seen. Only took centuries to develop parallax from a theoretical concept to a practical technique to a routine measurement. Only took decades more to automate the process, to build spacecraft that measure parallax for billions of objects, to achieve micro-arc-second precision that reveals the galaxy's structure, and now those precise distances feed into equally precise predictions of non-detectability, calculations that prove certain observations aren't worth attempting because the signal lies too far below the noise. The precision serves to bound ignorance from both sides, knowing what can be measured and what cannot. Microlensing as a detection method emerges from the realization that you don't always need to resolve multiple images or measure precise deflection angles. When a massive object passes between Earth and a background star, the star's light is magnified even if the images remain unresolved. The star appears brighter for a period of time, then returns to normal as the geometry changes. This brightening event carries information about the lensing object's mass, distance, and velocity, encoded in the light curve shape and duration. The phenomenon was predicted theoretically in the 1960s, but practical detection required technological advances that came later. You need to monitor millions of stars continuously, looking for rare brightening events among the vastly more common variable stars, supernovae, and instrumental artifacts. Only in the 1990s did CCD detectors and automated telescopes make such monitoring feasible. The first microlensing event was detected in 1993, a star in the Large Magellanic Cloud brightening and fading over weeks as an unseen foreground object passed in front of it. The light curve has a characteristic shape, symmetric and smooth, described by a simple formula involving the impact parameter, how close the lens passes to the line of sight, and the Einstein radius. When the lens is far from alignment, magnification is negligible. As alignment improves, magnification increases. At closest approach, magnification peaks. Then, as the lens continues moving, alignment worsens again and the star returns to its original brightness. The entire event is achromatic, all wavelengths brighten equally, distinguishing it from intrinsic stellar variability, which often shows color changes. The time scale of the event depends on the Einstein radius and the relative velocity between lens, source, and observer. For a solar mass lens at typical galactic distances moving at typical galactic velocities, the Einstein radius measures a few milliarc seconds, and the crossing time is weeks to months. For a Jupiter mass lens, the time scale drops to days. For an Earth mass lens, hours. For a Moon mass lens, minutes. Below that, events become so brief that they're difficult to distinguish from noise in photometric data. Thousands of microlensing events have been detected in surveys monitoring the galactic bulge, where dense star fields provide millions of background sources and foreground stars are common enough that alignments happen regularly. Each event reveals the Einstein radius timescale through the light curve shape, but converting that timescale to an actual mass requires knowing the lens distance and velocity, which are usually unknown. Most microlensing events remain dark. The lensing object isn't visible, either because it's too faint or because its light is overwhelmed by the brighter source star. Additional information comes from detecting parallax in the microlensing event itself. As Earth orbits the Sun during a long-duration event, the changing observation angle causes small deviations from the simple, symmetric light curve. Modeling these deviations yields the lens distance, which combined with the Einstein radius timescale determines the mass. This works well for events lasting months, where Earth's orbital motion creates measurable parallax effects. Planets orbiting the lensing star create distinctive signatures. The planet produces a brief additional magnification spike lasting hours to days, superimposed on the weeks-long stellar magnification curve. The spike's duration and amplitude depend on the planet's mass and orbital radius. This technique has discovered hundreds of exoplanets, many at orbital distances too large for radial velocity or transit methods to detect. It's particularly sensitive to planets at a few AU from their stars, filling a demographic gap in planet surveys. Some microlensing events show binary lens effects, where two stars in a binary system each contribute to the lensing. The light curves become complex, with multiple peaks and unusual shapes that require sophisticated modeling to interpret. But these complex events provide rich information mass ratios of the binary components, projected separations, sometimes even orbital motion if the event is monitored long enough and carefully enough. Free-floating planets, worlds not bound to any star, drifting independently through the galaxy, create very brief microlensing events. Their masses are typically Jupiter scale or smaller. Their Einstein radii measure micro-arc seconds, and event durations are hours at most. Detecting such brief events requires high-cadence monitoring, observing each star multiple times per hour to avoid missing the peak. Several candidate free-floating planet detections exist, though confirming their planetary nature versus other explanations remains challenging. The key requirement for microlensing detection is sufficient magnification to rise above photometric noise. If a star brightens by 1%, that's detectable with good photometry. If it brightens by 0.001%, that's at the noise limit for most surveys. Magnification depends on alignment quality through a specific functional form. Maximum magnification occurs when the source passes directly behind the lens, and magnification drops rapidly as the impact parameter increases beyond a few Einstein radii. For an alignment where the impact parameter equals the Einstein radius, magnification reaches approximately 1.34, or 34% brightening easily detectable. For impact parameter twice the Einstein radius, magnification drops to about 1. Straw 7 or 7% brightening still detectable with careful photometry. For impact parameter 10 times the Einstein radius, magnification is only 1.001 or by 0.1% brightening lost in noise. This means the detection probability scales roughly as the Einstein radius squared. Double the Einstein radius, quadruple the detection probability, because you've quadrupled the cross-section for alignments close enough to produce detectable magnification. The Einstein radius itself scales as the square root of mass, so detection probability scales linearly with mass double the mass, double the chance of detection. For 3I Atlas, the Einstein radius for background stars at galactic distances is approximately 10 fem2 seconds. Converting this angular scale to a physical cross-section at the object's distance yields roughly 40 meters. That's the radius of the circle in which a background star's center must fall for any detectable magnification to occur. The object itself is perhaps 2 kilometers in diameter, but the lensing cross-section is 40 meters 10,000 times smaller in area. The number of background stars potentially affected can be estimated from star density in the region where 3I Atlas moves. Typical star surface densities in high galactic latitude fields are roughly 1 per square arc minute. 3I Atlas moves at about 100 arc seconds per day relative to background stars, sweeping through an area of perhaps 0.01 square arc minutes per day. That's 1 star every 100 days, on average, close enough that the object passes within a few arc minutes. But passing within arc minutes isn't enough. You need the star to fall within femtoarc seconds, a factor of billion times smaller angular scale. The probability is roughly 10 to the minus 18 per star. With 1 star per 100 days, you'd need 10 to the 20 days 100 billion days, far longer than the age of the universe to expect one detectable event. Even this pessimistic estimate is optimistic in assuming perfect photometry and continuous monitoring. Real surveys have detection thresholds, gaps in coverage, instrumental problems, brief events lasting seconds. The expected duration for 3I Atlas microlensing given its velocity are particularly difficult to detect reliably. Most surveys observe each field every few hours at best, easily missing sub-minute events entirely. Some specialized high-cadence surveys exist, monitoring smaller numbers of stars more frequently. These are designed for detecting stellar flares, eclipsing binaries, or other short timescale phenomena. But even monitoring every few seconds, a femto-arc-second Einstein radius means negligible detection probability. The alignment requirements are simply too stringent, the cross-section too small, the probabilities too unfavorable, and yet microlensing remains a proven technique for objects with sufficient mass. It has detected stellar remnants, brown dwarfs, exoplanets, possibly free-floating planets. It probes mass ranges and orbital distances inaccessible to other methods. It will continue finding objects as surveys improve and extend to longer baselines and higher cadences. But there are lower limits to detectability, thresholds below which even perfect observations cannot overcome geometric improbability. 3I Atlas sits well below those thresholds. Its mass places it in a regime where microlensing becomes theoretical rather than practical, calculable but not observable. The equations predict magnification factors differing from unity by parts per trillion for the best possible alignments. The probabilities predict waiting times exceeding cosmic age by vast factors. The technique that works brilliantly for solar mass lenses and adequately for planetary mass lenses fails completely for asteroid mass lenses. Only took decades to develop microlensing from theoretical prediction to routine discovery method. Only took a few more to detect planets through their lensing signatures, to probe the galactic mass distribution, to find objects invisible through any other technique. And still, there are mass scales it cannot reach. Objects too small to create detectable effects, no matter how favorable the geometry or how perfect the observations. The universe allows the effects to exist while preventing their detection, maintaining a boundary between principle and practice that no observational advancement can fully erase. The sky appears sharp to human eyes, stars rendered as points against darkness. But this sharpness is illusion, artifact of limited angular resolution in the human visual system. Stars are not points. They're distant suns with physical sizes, though even the nearest appear smaller than milliarc seconds when viewed from Earth. What humans perceive as points are actually diffraction-limited images. the smallest spots that light can form when passing through the eye's aperture. Atmospheric turbulence degrades this theoretical limit dramatically. Air masses at different temperatures and densities create refractive index variations. Light passing through these variations bends unpredictably, causing stellar images to dance and blur. The effect, called seeing, limits ground-based angular resolution to roughly 1 arcsecond under good conditions, worse when turbulence is strong. Adaptive optics systems partially compensate by measuring wavefront distortions and correcting them with deformable mirrors, achieving angular resolutions near the diffraction limit for bright guide stars. From space, atmospheric seeing doesn't exist. The Hubble Space Telescope achieves angular resolution near 0.05 arcseconds in visible light, limited by diffraction through its 2.4-meter aperture. The James Webb Space Telescope, operating at infrared wavelengths with a 6.5-meter aperture, achieves even finer resolution in arcseconds despite the longer wavelengths partially offsetting the larger aperture. These space-based capabilities reveal details invisible from the ground substructure in galaxies, multiple images in gravitational lens systems, disks around young stars. But even these capabilities fall short for detecting deflections by 3i Atlas. The predicted deflection, roughly 2 micro-arcseconds for the closest possible passes, is 50 times smaller than Hubble's resolution and 1,000 times smaller than typical seeing-limited ground observations. No amount of exposure time or signal averaging can recover information below the diffraction limit or atmospheric seeing disk. The blur is fundamental, set by wave optics and atmospheric physics, not something that vanishes with better detectors or longer integration. Interferometry offers paths to higher resolution. By combining light from telescopes separated by large distances, astronomers create synthetic apertures much larger than any single telescope. The resolution becomes limited not by individual telescope size, but by baseline, the separation between telescopes. Very long baseline interferometry using radio telescopes separated by thousands of kilometers achieves micro-arc-second resolution, revealing structure in quasar jets and nearby stellar surfaces. Optical interferometry faces greater challenges. The wavelengths are shorter, requiring path length matching to within nanometers. Atmospheric turbulence affects each telescope independently, making coherent combination difficult. Still, facilities like the Very Large Telescope Interferometer achieve millisecond resolution for bright sources, enough to resolve stellar diameters and binary separations. Future systems might push toward micro-arc-second scales with larger baselines and better adaptive optics. Even then, detecting 3i Atlas lensing requires more than just angular resolution. You need differential astrometry measuring how star positions change as the object passes nearby. This requires either repeated observations to establish pre-event positions or simultaneous observation of multiple reference stars to provide a coordinate frame. Both approaches face systematic errors, telescope pointing drifts, optical distortions, detector effects, reference star proper motions, parallax corrections. The Gaia spacecraft achieves micro-arc-second astrometry through specialized design. 2 telescopes pointing in different directions simultaneously observe overlapping star fields. Each star is measured dozens of times over years as the spacecraft scans the sky continuously. Sophisticated calibration models remove instrumental systematics. Repeated observations average down random errors. The final positions achieve 20 micro-arc-second accuracy for bright stars, with proper motions and parallaxes determined to similar precision. But Gaia observes each star according to a predetermined scanning pattern, not targeting specific objects for rapid cadence monitoring. The spacecraft cannot be redirected to observe stars near 3I Atlas with the frequent repeated measurements needed to detect brief deflection events. And even if it could, the deflections remain 10 times smaller than Gaia's single measurement precision, detectable only through extensive averaging that the brief event time scale prohibits. Geometric dilution also works against detection. A star at 1 kiloparsec distance is roughly 200 million AU from Earth. The physical separation corresponding to 1 microarcsecond at that distance is 0.0005 AU, about 750,000 kilometers. Light from different parts of the star's surface travels slightly different paths through 3A Atlas's gravitational field, experiencing slightly different deflections. This differential deflection smears the lensing signal over the star's angular size. Most stars sub-10 microarcseconds or less at kiloparsec distances, so this smearing is minor compared to other effects, but it illustrates another way. Nature limits lensing detectability, sources have finite size. Lenses have spatial extent, alignments are imperfect, and all these factors combine to reduce signal below idealized point source. Point lens calculations, instrumental limitations compound. CCDs have finite pixel sizes, typically 0.1 to 0.5 arcseconds per pixel for wide-field survey cameras. Measuring star positions requires fitting models to multi-pixel images, interpolating to find centroids to sub-pixel precision. Photon noise limits centroid accuracy. Roughly the point spread function width divided by the square root of detected photons. For milliarc-second precision, you need tens of thousands of photons per star. For microarc-second precision, hundreds of millions. Faint stars simply don't provide enough photons. A magnitude 20 star delivers perhaps 100 photons per second to a 1-meter telescope. Achieving microarc-second centroid precision would require hours of integration, by which time 3I Atlas has moved and the geometry has changed. Bright stars provide more photons but are rarer, and the probability that one lies along the object's path with sufficiently precise alignment remains negligible. Chromatic effects introduce additional complications. Atmospheric refraction bends light from stars, with the amount depending on wavelength and elevation angle. Different colors appear at slightly different positions, typically tens of milliarc-second separation between blue and red ends of the spectrum. Gravitational lensing, being achromatic, affects all colors equally. But measuring star positions requires choosing a wavelength band, and atmospheric refraction differs between observations at different times when stars are at different elevations. From space, atmospheric refraction disappears, but other chromatic effects remain. Optical systems have wavelength-dependent aberrations. Detector quantum efficiency varies with wavelength, weighting centroids differently for stars with different colors. These effects are small, correctable with calibration, but they add systematic uncertainties at the microarc-second level. When the signal you're seeking is microarc-seconds or smaller, these systematics matter. The combination is decisive. Atmospheric seeing blurs star positions by arc-seconds. Adaptive optics and space telescopes reduce this to tens of milliarc-seconds. Interferometry and specialized astrometric missions reach microarc-seconds for bright sources with long averaging times. But 3Y Atlas's deflections are sub-microarc-second, briefer than integration times, and apply to random background stars that are usually too faint for high-precision astrometry. Every technical capability has limits. Telescopes cannot be arbitrarily large due to engineering and cost constraints. Detectors cannot be arbitrarily sensitive due to quantum noise and dark current. Baselines cannot be arbitrarily long without losing coherence. Observations cannot be arbitrarily precise due to photon statistics and systematic errors. These limits interact, creating boundaries to observability that some phenomena fall beyond. 3i Atlas's lensing signature falls beyond those boundaries, not barely by orders of magnitude. Not temporarily, no foreseeable technological advance will close the gap between sub-micro-arc-second signals and milli-arc-second precision typical for faint sources. The boundary is firm, defined by physics and engineering, unlikely to shift dramatically even with space-based interferometers or future astrometric missions. The sky stays sharp. Then, not because 3i Atlas fails to curve spacetime, but because its curvature is too subtle to distort the images that reach our detectors. Stars remain in their catalogued positions to within measurement uncertainties. No brightening events occur as the object passes between Earth and background sources. The absence of signal is not evidence of absence of effect. The effect exists, predicted reliably by general relativity. The absence reflects instead the relationship between cosmic scales and technological capabilities, between what nature allows in principle and what instruments reveal in practice. Only took centuries to progress from naked eye observations limited by physiology to space-based astrometry limited by photon statistics. Only took decades more to develop interferometry pushing toward micro-arc-second scales for the brightest targets. And still, some effects remain invisible, some deflections too small, some objects too insignificant gravitationally to distort the sky in ways current or foreseeable instruments can detect. The universe sets the scales. Technology approaches them asymptotically. And 3i Atlas operates well beyond the asymptote's current reach. Dark matter does not emit light. It does not absorb light. It does not interact electromagnetically at all, as far as observations can determine. Its presence is inferred entirely through gravitational effects, rotation curves of galaxies that remain flat instead of declining with radius, velocity dispersions in galaxy clusters too large for the visible mass to contain, gravitational lensing stronger than visible matter alone can produce. The evidence accumulates across scales. In individual galaxies, stars orbit faster at large radii than visible matter's gravity can explain. Either Newton's laws fail in low acceleration regimes, or additional unseen mass provides the gravitational pull. Modified gravity theories attempt to explain the observations without dark matter, but they struggle to match the full range of data, particularly from galaxy clusters and cosmological structure formation. Galaxy clusters present especially compelling evidence. The bullet cluster, a system of two galaxy clusters that collided and passed through each other, shows clear spatial separation between the visible matter, primarily hot gas emitting X-rays, and the gravitational mass mapped through weak lensing. The gas, being diffuse, experienced drag forces during the collision and slowed down. The dark matter, being collisionless, passed through unimpeded. The lensing maps show mass concentrations offset from the gas, exactly as dark matter models predict. This dark matter, whatever it is, curves space-time substantially. A typical galaxy cluster's dark matter halo masses hundreds of trillions of solar masses, creating Einstein radii measured in tens of arc-seconds for distant background sources. These are the scales that produce spectacular gravitational arcs, multiple images, and strong magnification effects visible in Hubble images. The dark matter's gravitational lensing provides the primary tool for mapping its distribution, revealing how it clusters and how it relates to visible galaxies. On smaller scales, individual galaxies are embedded in dark matter halos, massing perhaps 1 trillion solar masses for Milky Way-sized systems. These halos extend far beyond the visible stars. their density dropping gradually with radius according to profiles measured through rotation curves and satellite galaxy